Okay, this is the last of our notes for section 2.3 for pre-calc. You will need a graphing calculator for these examples, so go ahead and get that out and be ready to pause the video when I ask you to stop and try something on your calculator. All right, example 9. It says Dixie Packaging Company has contracted to make boxes with a volume of approximately 484 cubic inches. Squares are to be cut from the corners of a 20-inch by 25-inch piece of cardboard and the flaps folded up to make an open box. What size squares should be cut from the cardboard? So if we think about our picture, all right, we have a 20 by 25 inch piece of cardboard and we are cutting little squares out of the corners, and they said to make those squares X inches on each side. All right, so if we look at a volume model, because we're trying to get a volume of 484 cubic inches, volume is length times width times height, and so we need to look at what would this box be if we just used this part of it. All right, so we're cutting out the squares in the corners and then we're folding it up. So our dimension here is going to be 25 minus the 2 x's that we're cutting off the sides. And then our dimension on this direction is going to be 20 minus 2x, since for the same reasoning, we're taking an x off of each side of it. So it's no longer 20 inches wide. So our volume model is going to be an x for our height, because that's the portion that we're folding up, and then our lengths and widths, we've got a 20 minus 2x and we have a 25 minus 2x. And for this example, I'm going to let you go ahead and leave it in factored form like that. In our next one, I'm going to ask you to multiply it out. All right, and then the question says we want to have a volume of 484. So we're really looking for, when does x times 20 minus 2x times 25 minus 2x, when does that give us 484 cubic inches? So on your calculators, I want you to type in y1 is 484 and y2 is this equation x times 20 minus 2x times 25 minus 2x. Go ahead and type that in. For our window, we are going to go from 0 to 10 for x's and from 0 to 900 for our y values. Excuse me. So let's look at, why did I stop at 10? Because I have the shortest side of my cardboard is 20 inches. And if I took 10 inches off of each side, I'd have nothing left. So the maximum x value that I could use would be this 10. And then volume, we're looking for as our y coordinate. I just set it up at 900 to make sure I can get past this 484 that I'm trying to see. So go ahead and take a minute, type it in your calculator, and set your window to these dimensions, and then let's look at what we've got. All right, just a rough sketch. You should have seen something like this, and your 484 coming across as a straight line. So there are 2 points where our volume ends up being 484. That means that we can actually make 2 boxes that have a volume of 484. One is if we cut out squares that are 1.22 inches long, and the other option is if our squares are 6.87 inches long. It just depends on if we want a shorter height and a bigger base to it, or if we want a smaller base and a taller box. Okay, so this would be our 1.22 and this would be our 6.87 option. All right, in both cases we get that volume of 484. All right, with our example 10, again, they've given us the same type of picture. All right, so example 10 again, they've given us that same type of picture. We have a 20 centimeter by 40 centimeter piece of cardboard this time, and again, we're cutting those little squares out to make a box. So if we think about our dimensions, our height here is x, And we would have 40 minus 2x as our longer side and 20 minus 2x as our shorter side. So again, our volume equation, length times width times height, we have a height of x, and we have a width of 20 minus 2x, and a height, length of 40 minus 2x. Okay? For this one, it says write an equation in expanded form. That means we want you to go ahead and multiply that all out. So if we were to FOIL out the two binomials, we would get 800 minus 120x plus 4x squared. And then if we distribute our x and put it in standard form, we end up with 4x cubed minus 120x squared plus 800x. Okay, so part A is finished. Part B, it says, what is the domain of v of x? So if we just look at our equation here, our domain would be everything. Okay, but then it says, for what values of x is the volume positive, greater than 0, and what is the relevant domain? That is, what values of x make sense in the context of this problem? So again, if you think back to our piece of cardboard, our shortest side was 20. And if we start going in from either side, the maximum that we could cut off would be 10 centimeters, or we wouldn't have anything left to use. All right, so our domain for v of x would be all reals, but our relevant domain, based on our actual context of the question, would be from 0 to 10. We can't take off anything negative, and we can't go past 10. Okay? Part C. If the volume of the box is to be 1,500 cubic centimeters, it says show that the box can be constructed in two different ways and find the exact dimensions of the box in each case. So it's going to be a picture like we had in our last example, where there's two options that give us a volume of 1,500. All right, so if we think about graphing this, an appropriate window, again, 0 to 10 for that relevant domain. And then since we're trying to get up to seeing 1,500, let's go up maybe to 2,000. All right, so we are going to put in 1,500 equals our equation 4x cubed minus 120x squared plus 800x. Again, we're going to put this in as y1 and as y2 for that side and look for where they cross. So again, we have that piece of our cubic graph, and we're coming across at 1,500. Okay, so pause the video for a minute and find these two spots. Okay, so using an intersect feature, it intersects at x being 5. We get 1,500. And then we have another point of intersection at 3.486, 1,500. All right, so there's two options where we would get a volume of 1,500. One option is we can cut out a square that is x centimeters. So 5 centimeters is our first option. And if we do that, and we go back to our equation, using 5 for x, if we put a 5 in here, we've got 20 minus 10, which would give us 10, and then we've got 40 minus 10, or 30. So our dimensions of our box would be 5 by 10 by 30. And the other option was if x, we'll just round to 3.5 centimeters, plugging in 3.5. Timesing by 2 gives us 7. 20 minus 7 would be 13. And 40 minus 7 would be 33. So our last option, we have a 3.5 by 13 by 33 for our box. And then the last question says, what dimensions will give the maximum volume for the box? Sorry, I guess this information should have been up here for part C. I'll have to extend my page here. All right, so part D. What dimensions will give the maximum volume of the box? So now we're trying to find this piece up here, right? We want that maximum point. So using your calculator, go ahead and pause the video and find your maximum. All right, we should have had a maximum of 1,539.6 cubic centimeters when we cut out a square where x is 4.226 centimeters. All right. Then our last piece, we are looking at some other types of regression equations. It says, just as any 2 points in the Cartesian plane with different x values and different y values determine a unique slant line and its related linear function, any 3 non-collinear points with different x values can determine a quadratic function. In general, if you have n plus 1 points positioned sufficiently generally, determine a polynomial function of degree n. In other words, if you want a 4th power function, you would have to know 5 points. All right, you always need 1 point more than the degree you're looking for. The process of this is called polynomial interpolation, and we're going to try 2 different ones. We are going to take some data, and first of all, we're going to do a cubic regression, and our second one is a quartic regression. And I'm going to have you pause the video and go ahead and try those. It's just like doing a linear or quadratic regression. So we're going to put x's in list 1 and y's in list 2. And then you just want to tell it to do a cubic regression instead. And then the same thing for question 2. So go ahead and pause the video and try those 2, and then turn the video back on and check your answer. Okay, for our cubic regression, you should have had an equation y equals 0.00614 x cubed plus 0.0177 x squared minus 0.5007 x plus 0.977. All right, and if you looked at your r values, you had an r squared of 1, which means it's a perfect fit. So your graph should have gone through your points exactly. And then for the quartic regression, we had 5 points, so we could find a quartic regression. Y equals negative 0.375 x to the 4th plus 6.917 x cubed minus 44.125 x squared plus 116.583 x minus 111. And again, your r squared value is 1, which means a perfect fit. All right. In general, you're trying to always pick a model with the least or lowest possible degree that has a reasonably good fit. In other words, if you have 5 points, but you can get a cubic model to be a very good fit, then you'd want to use that. You don't want to use the quartic model if a cubic would work. All right. For your third day's assignment, you are doing 53 to 56, 58, 59, 63, 65, 66, 75, and 83.